Welcome back to Even More about resistance. In particular, we want to know if you have more than one light bulb, how does that change the resistance? Does it make it more resistant, less resistant? What are the different ways that you could connect light bulbs together if you have more than one? These and other questions will be addressed here. Well, in Activity 3, we were introduced to multiple ways to connect up multiple light bulbs. And one way to do it, of course, is to just make one path. So no matter how many light bulbs you have, you just make one path for them. And the name of this, when you have one path, is called a series circuit. Now, when we did this, what we learned is both looking at the compass and looking at the brightness of the light bulbs, it appeared that the more light bulbs that I had in series, the dimmer that the light bulbs became, and the less that the compass deflected. So both of those things, compass deflecting less, light bulbs being dimmer, the more light bulbs I put in, indicates less flow rate. So the more light bulbs that I put in series, the lower the flow rate. Now we tried to mimic this as well by using straws. Notice these straws are also in series. We make one path. All of the air has to go through all of the straws, just like all of the charge in this circuit has to go through all of the light bulbs. And compared to just one straw, blowing air through 4 straws is more difficult. So we found that as you increase the number of resistances, which is what light bulbs are, in series, you increase the overall resistance. Likewise, another way to connect multiple light bulbs or resistors is to have multiple paths. In series circuits, you have one path. In parallel circuits, each light bulb actually has its own path. So if charges were to go through this circuit, they could go through this light bulb, or they could go through this light bulb, or they could go through that light bulb. They could go through any one light bulb. They don't have to go through all 4 light bulbs. Multiple paths. And we also mimic that with straws by having 4 straws all together in a bundle. So if you're blowing through these, air leaving your mouth only has to go through one straw. And we found that the more light bulbs that you put in parallel, the easier it is for charges to get through the whole network. So when you discharge the capacitor through 2 light bulbs like this, you found that it actually took longer to discharge it than through 4. And if we had had 5 or even 6 of them, it would have even been less time. So because the amount of time that it takes for a capacitor to discharge through light bulbs indicates the resistance of the light bulbs, we would say that the more light bulbs you put in parallel, the lower the overall resistance. The more light bulbs you put in series, the higher the overall resistance. So to summarize this, we said in a series circuit where there's only one path, all of the moving charge has to go through every resistor. There's no choice because there is only one path. So that means every part of the charge is resisted every time that it passes through a resistor. In a parallel circuit, the moving charge is split into parts. Each part will pass through only one resistor, so its motion is resisted only once. In a series, the resistor charge is resisted every time it goes through a resistor. Here it's only going to be resisted once because it only has to go through one light bulb or one resistor. So when I add resistances in series, the multiple resistances act like a single longer resistor. Because every charge has to go through every resistor, it's as if you had one big long resistor. And if you remember our formula for resistance, where we had resistivity times length divided by area, if I have a longer resistor, I have more resistance. If I have more resistance, it makes the flow harder. So I saw this with the straws. If I put the straws all in one path, the more straws I have in a row, the harder it is to get air through them. Now if I put resistors or light bulbs in parallel, it acts like one thick resistor. and it makes the flow easier. Now we also saw this in this formula, resistivity length over area, that if I increase the area or the thickness of the wire, the resistance decreases. Area is in the denominator. The larger the area, the less resistance. It's easier to get air through a bunch of straws instead of one long straw. And in fact, the more straws I add in this bundle, the easier it's going to be for air to get through. The more resistors I have in parallel, the easier that it is for charges to get through. Now let's apply this idea of series and parallel resistances to toll booths. One toll booth I could think of as a resistor, that when cars are trying to get down the highway, they have to slow down, hopefully, to get through the toll booth, so toll booths will impede the motion of a car. Now notice here I have multiple toll booths. So knowing that toll booths slow cars down, what if it's my first day at work, I'm a brand new toll booth operator, and I show up for work, and my boss looks out the window and notices that cars are really beginning to build up behind the toll booth, and there's only 3 of these booths open. So my boss tells me to go out and open another booth. But I am a little bit confused because I think, wait a minute, if toll booths slow cars down, and the problem is that the cars are backing up, why does opening another toll booth, which slows cars down, why will that help? Until I realized that, yes, one toll booth slows a car down, but if I open multiple toll booths, I actually improve the flow by making multiple paths. These toll booths are in parallel. In other words, there's multiple paths. Imagine how ridiculous it would be to have a toll plaza where the toll booths are in series. Because if I had toll booths in series, the car would have to stop through every toll booth. I'd have one after the other, after the other, after the other. Opening more toll booths if they were in series would certainly make the problem worse. But opening more branches, opening more toll booths, even though an individual toll booth does slow a car down, having more of them open provides multiple paths, so the overall resistance of the toll barrier actually decreases to traffic the more of these I have open. So if I only had one open, that would be a very large resistance to traffic flow. But if I open another one, even though it's a resistance, then I have decreased the resistance of the toll barrier to traffic. And if I open them all, that is the least amount of resistance to traffic flowing through. So the more resistors I have in parallel, the lower the overall resistance. As I continue to add more, I'm lowering the resistance. More resistors I have in series, I actually increase the resistance overall, because every charge or every car would have to go through every resistor. So now the question is, how do we calculate the resistance of a group of resistors, whether they are connected in series or connected in parallel? Well, these two formulas are on the reference tables, and this formula tells me that if I have multiple resistors, in this case 3, and I want to figure out what the overall resistance, and we have a special name for that, the overall resistance is called the equivalent resistance. And that means what one resistor is equivalent to the 3 resistors that you've put in this case. Well, for series, that's pretty easy. I know that the more resistors I put in series, the larger the overall resistance, and it turns out that because charges go through each resistor, the overall or equivalent resistance is just the sum of the 3 resistances added together. Now for parallel, it's a little more complicated because I know that the more resistors I add in parallel, the lower the overall resistance. So when I add resistances up in series, it makes the resistance go up. But now, this formula, when I add these resistors, it makes the overall resistance go down. And notice that these are all reciprocals. So let's try a problem together. Okay, let's try this problem. Calculate the equivalent resistance for 3 4-ohm resistors if they are connected in series and in parallel. Let's do the series first. Formula for calculating equivalent resistance in series is equivalent resistance equals R1 plus R2 plus R3. So I have 3 4-ohm resistors, so it would be 4 ohms plus 4 ohms plus 4 ohms, which is going to be 12 ohms. So that wasn't so bad. Let's try the parallel one now. Well, in parallel, the formula looks like this. 1 over the equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. So 1 over R equivalent is going to equal 1 over 4 ohms plus 1 over 4 ohms plus 1 over 4 ohms. So now I have to remember how to add fractions. Well, I need a common denominator, which I've got. It's 4. So 1 over 4 plus 1 over 4 plus 1 over 4 is 3 over 4 ohms. So I can say 1 over the equivalent resistance is 3 over 4 ohms. Now, the mistake that can frequently be made is that when I do this addition here, so I get 3 over 4 ohms, I think that's the answer. But it's not the answer, it's 1 over the answer. I want that. I want R equivalent. So I'm going to cross multiply, and I end up with R equivalent equals 4 ohms over 3. So the answer to the question, what is the equivalent resistance for 3 4-ohm resistors connected in parallel, is actually 4/3 of an ohm. In other words, a little over 1 ohm. And notice that that resistance is less than any of the individual resistances that make it up. And that's what we saw before, that the more of these 4-ohm resistors that I put in parallel, the lower the equivalent resistance gets. If I add a 4th one, then I'm going to have 4 over 4 ohms. This number would be 4 over 4, so then I'd only have 1 ohm. So 4 4-ohm resistors in parallel only have 1 ohm of resistance. Okay, now it's your turn. Okay, so you try this problem and then show me the solution when you come back to class. Calculate the equivalent resistance of 3 12-ohm resistors if they're connected in series and also if they're connected in parallel.